Our problem is to evaluate this integral x dx dy over the region R, where R is the set of pairs of points where the first number goes from 0 to 4, the second number goes from 0 to 8 minus the first number. Normally we would draw a picture of the region to get a kind of a game plan of how we're going to integrate, but here we're given the bounds for each variable, so we can just plug that in. We have x dx dy. X is the first variable of integration, so we're going to check that it goes from 0 to 4, and put those in the first bounds. And then y, the next variable, goes from 0 to 8 minus x. We'll put that in there. There's a problem here. The problem is that x is just a dummy variable. The only place that is relevant is for this integral over x. I'm going to call this the scope of x, the place where it's relevant. And so this is invalid because x is outside scope. There's an easy way to fix this. Just like we can sum numbers in any order we want, we can also integrate in any order we want. So you can switch the x and y. We'll do y first and then x. There's still an x up here, but this is okay since this x is within the whole, this is the scope of x now. The outside integral is over x, and every time x occurs is within that integral. All right, now all we have to do is evaluate. You can integrate this first integral first. Over dy, you have xy evaluated from y equals 0 to 8 minus x. And so that's that first integral. We're still integrating on the outside from 0 to 4. And all right, so evaluate this as y goes from 0 to 8 minus x, and you get x times 8 minus x minus a 0. And now you can expand it. Let's expand this into 8x minus x squared, and then integrate 8x. We will get 4x squared. You integrate x squared, you get x cubed over 3. I'm going to evaluate that from 0 to 4. Okay, so now we plug in 4. We get 4 times 16 is 64 minus x minus 4 cubed over 3, 64 over 3. And then when you plug in 0, you get 0. So minus 0. This comes out to 64 times 2/3, or 128 over 3. Oh, there it is.